Hello and welcome to this lesson for Chemistry 20 in the gases unit. Today we're going to move on to something called the combined gas law and look at the formula and calculations that we use when we are going to have all three of our variables manipulating. Not manipulated, one is manipulated and the other ones are responding, but essentially we are going to take into consideration all three of our variables: pressure, temperature, and volume. Right? When we had just volume and pressure, it was Boyle's law. When we had just volume and temperature, it was Charles' law. But what about when we have all three? All three combined together to make what's called the combined gas law. Now, in these questions, you may be told you have STP or SATP conditions. STP stands for standard temperature and pressure, which means you're at sea level and 0 degrees Celsius. Okay, so that would be 273.15 Kelvin and sea level is 101.325 kilopascals. That's if you're told you're at standard temperature and pressure, STP. If you're told that you are at SATP conditions, that stands for standard ambient temperature and pressure, meaning more room-like conditions. So room temperature is defined as 25 degrees Celsius, and the pressure is a little bit above. It's actually 1 bar, if you remember to the conversion between a bar. It's at 100 kilopascals and 298.15 Kelvin. Okay, so if we look at our two formulas, I'm actually just going to take that away for a second. So we know Boyle's law is P₁V₁ equals P₂V₂. And we know that Charles' law was V1 over T1, that's not a 1, equals V2 over T2. That's the original formula for Charles' law. When we put them together, this gives us our combined gas law. Now again, we don't like using these formulas as fractions. So I'm going to cross multiply it so that it's one nice linear formula. So it'll be P₁V₁T₂ equals P₂V₂T₁. Okay? So the temperatures again are on opposite sides of the ones and the twos. P₁V₁T₂ equals P₂V₂T₁. Now technically, if you just memorize this formula, it has all the formulas together in there. So what I'm saying is, let's say you have a question where only pressure and volume are given, temperature is constant. You would omit the temperature, and there you have Boyle's law. Okay? If you have a question with temperatures and volumes, and there's no pressure, you would omit the pressures and get Charles' law. What happens if you have a question where the volume is constant? The volume is not changing. You have only pressures and temperatures. You could omit the volumes and get something called the Gay-Lussac law, which I don't commonly teach in regular Chem 20. But if you have a constant volume, which means a confined space, remember we talked about how when you increase temperature, if the volume cannot change, the pressure increases. So that would be how you can do a calculation of a confined space. You can either leave volume in the calculation and keep V1 and V2 as the same number, or just omit it from the formula. Now our pressures, volumes, and temperatures again. Our pressures need to be in kilopascals, our temperatures need to be in kelvins, and our volumes need to be in liters. Okay? So if we go through and look at some examples. A weather balloon is filled with hydrogen gas at 20 degrees Celsius and 100 kilopascals with a volume of 7.5 liters. Okay, so I can make these my ones. This will be my T1 after I add 273.15. This will be my P1, because that was kilopascals, kind of got cut off there. And this will be my V1. It rises to an altitude where the air temperature changes to -36. So that's my T2 once I add 273.15. And the new pressure, P2, is 28. It wants to know the new volume. What is V2? Okay, so we have a lot of numbers here. So making a little chart for us, listing our variables is very helpful. So 20 plus 273.15 is 293.15 Kelvin. Our P1 is in the units it needs to be, kilopascals. And our V1 is in the units it needs to be, 7.50 liters. Okay? Our T2, negative 36 plus 273.15, oops, I multiplied. Negative 36 plus 273.15 gives us 237.15 Kelvin. Our P2 is 28 kilopascals, and V2 is what we are solving for. Okay, lots and lots of variables here. So my formula is P₁V₁T₂ equals P₂V₂T₁. We have 3 variables here, big long formula. I'm actually going to arrange this formula first because it might be a little easier than having to move a whole bunch of numbers. So I am solving for V2. And right now V2 is multiplied by P2 and T1. So I need to divide both sides by P2 and T1 multiplied by each other on both sides. P2 times T1. Now this is really important when you put it in your calculator. If you don't use brackets around this entire calculation, P2 times T1, all in brackets, depending on your form of calculator, you may get the wrong answer, okay? So in the denominator, when there's multiplication happening, put it all in brackets. This is your safest bet, okay? So to solve for V2, we'll take P1, which was 100 kilopascals. We'll multiply it by V1, which is 7.50 liters, and multiply it by T2, which is 273.15 Kelvin. And then I'm going to divide that by P2. P2 is 28 kilopascals times T1, which is 293.15 Kelvin. So notice how, and again, when you're doing your calculations, whether you use brackets on the top or not, that doesn't matter. I could do multiplications like that and so on. I could put brackets around the whole term. It won't make a difference. But on the bottom, you have to have brackets on the bottom around the entire calculation, not just brackets around each one, but the entire calculation on the bottom needs to be in brackets, okay? So we would have 100 times 7.5 times 273.15. Oops, I think that I wrote that wrong. That should be 237.15. 237.15 divided by, in brackets, 28 times 293.15. So we get an answer for V2 of 21.668, so on. Let's look at our units. Our kilopascals cancel, our kelvins cancel. We're left with liters, which is what we need on the top for volume. Now, sig digs, I have 2 sig digs in my temperatures and 1 in my pressures. I have 3 in my volume and other pressure. The lowest is 2. So I'm going to keep it to 2 sig digs, these first 2 digits. It doesn't cut off the decimal, so I don't need to put it in scientific notation. But I am cutting off a 6, so it will round that 1 up to a 2. So it would be 22 liters for our final answer. Okay? Make sure, again, brackets around everything in the denominator, one big bracket. If you want to also have brackets like we did on the top before I changed it, you could have a bracket, then another bracket. 28 kilopascals times, what was it, T1, 293.15 Kelvin. So I could have those brackets, but then I need another bracket around the entire calculation on the bottom, okay? Or you can use your fraction button. Either way, make sure you get 22 as your final answer, okay? So that is our first example. Next example, you have a large syringe filled with 50 milliliters of ammonia gas at STP conditions. So remember we started that lesson looking at what STP meant. So I have my first volume. I'm going to convert it into liters though. To get from milliliters to liters, a milli is on your periodic table 10 to the negative 3. So you convert from milliliters to liters by multiplying by what a milli is equivalent to, which is 10 to the negative 3. Now that's also the same thing as saying I'm dividing by 1,000. Okay? To convert from milliliters to liters, you can just divide by 1,000. But if it was like a megaliter, a capital M, how do you convert, right? A mega is 10 to the power of 6. So you would multiply by 10 to the power of 6. So it's always important to know those SI prefixes. So STP is standard temperature and pressure. So that's my T1 and my P1. It's changing to a V2. Again, I'm going to divide by 1,000 to convert it into liters. And this is my P2. It wants my T2, final temperature. Okay, so if I list my variables, my V1 is 0.0500 liters. When I have 3 sig digs there, and I convert it by dividing by 1,000, I want to keep the same sig digs, which is why it's 0.500. Now, if you just write 0.5, it's fine, okay? But when I convert it, I like to keep the same sig digs in the number. My STP, the STP temperature is 273.15 Kelvin, and the STP pressure is 101.325 kilopascals. Remember that was at the first slide of this lesson. Our V2 is 0.025, and then if you add the 0 after it to make it keep 3 sig digs. The P2 is 210 kilopascals, and my T2 is what I am solving for. So let me again write my formula, and I'm going to again rearrange the formula first. P₁V₁T₂ equals P₂V₂T₁. I'm solving for T2, so I need to divide both sides by P1 times V1. And I need to put that in brackets. So T2 isolated is P₂V₂T₁ divided by P₁V₁ all in brackets. Okay? So my P2 is 210 kilopascals. My V2 is 0.0250 liters. And my T1 was 273.15 Kelvin. I will divide that by, open a bracket, and if you want to put another bracket inside, that's fine. My P1 is 101.325 kilopascals, and my V1 is 0.0500 liters. Close that initial bracket on the bottom, okay? So when we solve for T2, our kilopascals cancel, our liters cancel, we're left with kelvins. So 210 times 0.0250 times 273.15 divided by, open a bracket, 101.325 times 0.0500, close the bracket. We get an answer of 283.05, so on kelvins. Notice how the question asks in degrees Celsius. So I have to now subtract 273.15 to convert it back into Celsius. We do not start with Celsius, hoping we'll get an answer in Celsius. The relationship, remember, doesn't work like that. We always have to start with kelvins, get an answer in kelvins, then put it back into degrees Celsius if that's what it's asking for. Only if that's what it's asking for. So I get an answer of 9.906 so on degrees Celsius. And for sig digs, everything in the question has 3 sig digs. So I want 3 sig digs in my answer. The 6 is being cut off, so it's going to round that up. So my T2 is going to be 9.91 degrees Celsius as our final rounded with units answer. Okay? And I believe that is it for this pretty quick lesson on combined gas law. That would be it. Okay? So thank you very much for watching this video.